So I'll get started for the day because like I said last time, this lecture and the past lecture are like the most dense with the most information. And I don't want to end up going overtime on this one because I can't control when the video stops recording. So if you have any really important questions, go ahead and put your hand up. But there's a lot of stuff to cover in this lecture, and I just want to make sure I'm able to get through it all for the recording. So last time we talked about agents and environments, so things that live in environments, and then we kind of teased the idea that there's going to be problems. What is a problem? Well, we'll define exactly what a problem is today, and then talk about how we may implement an agent or a solution to a problem like that. So problem-solving agents, we talked last time about how rational agents maximize performance within some given performance measure. And so in the simplest case, you have to satisfy some sort of goal condition. This is called a satisficing problem, where you just have to do a thing, not necessarily optimize a thing. So for example, just reach the end of a maze, solve this crossword puzzle, etc. So a problem-solving agent is a type of goal-based agent. And what we want to do, essentially, is find a sequence of actions that satisfies the goal. So if we have a particular problem, the output of our function, of our search or neural network or whatever, is going to be a sequence of actions that takes us from the starting state of that problem to a goal state of that problem, if there are many, or the goal state if there's just one. So let's look at a sort of homegrown example here. So let's say that a tourist comes to Newfoundland and lands in St. John's. So hopefully you're all here, you're all familiar with the map of Newfoundland. So down here we've got someone who lands in St. John's, and that person wants to go to one of the following: either St. Anthony, which is up here in the very top. If you ever go for a vacation, it's a very interesting place to visit. Or they want to go to Port aux Basques down here, where there's a ferry that can take you to the mainland. But it's, both really interesting places in the province. But they want to go there, and they may have some sort of extra constraints on their problem as well. So for example, maybe you only have like 12 hours total to get there. And so maybe St. Anthony, maybe unless you're a speed demon, you can't get there in 12 hours. Maybe Port aux Basques is the only place that you can get to. Or maybe you only have a certain amount of money for gas, or basically any other thing that you can think of that may be a constraint on a given problem. So how do we know what our goal is? Well, some sort of goal formulation is necessary. So in this example, the goal would be one of a set of states in the environment. And so we have a set here of St. Anthony or Port aux Basques. These are the places that the person wants to go to. And so we know that the goal is satisfied if we get to one of the states of the environment where the agent is in one of these places. And so the goal is satisfied if one of them is reached. So a sequence of actions leads us to a goal state, or if a sequence of actions leads us to a goal state, then the goal has been satisfied and the problem has been solved. Now, this is not the case of an optimizing problem, necessarily, where you want to find the optimal solution, like the least gas or the least time, but this is just, okay, the goal has been satisfied. In this case, the goal is a set of states, and we would look at the state that the agent is in and just compare it to the set of goal states. But in general, this goal could be any arbitrary function that has to be evaluated, right? So for example, in a video game, maybe you've got if the enemy's health is less than or equal to 0, then you've defeated them, and maybe that's the goal. Or if you're playing chess, if the enemy is in checkmate. Or if you're playing something like Zelda, if the player has all the pieces of the Triforce and Ganon is defeated, right? So in general, this is a function that could be arbitrarily complex, but for this particular problem, it's just one of the two following states. So something that we have to consider when we go to formulate this problem in this environment is which states do we actually consider in our environment as valid states, right? So for example, if I'm talking about how to move around, like if I asked you, how do I get to that chair, right? You'd probably say, well, walk a couple of meters forward and turn to the left a little bit. But if I was asking to get to the engineering building, you probably would stop using local terms like walk a couple of meters, and you would say walk past the library, walk past the university center, turn right, go across the road. And so sort of the bigger your environment is, you'll have a lot of different ways to represent the actions that you can take. So for example, an action might be, hey, move 1 meter in a particular direction, or you may formulate actions as moving between towns. So go from St. John's to Clarenville, and you would have some assumed knowledge there that there might be a road connected between them or whatever. So which actions do we consider? Well, I just said that. You could consider moving left by a meter or a centimeter, moving from town X to town Y, moving from grid location X to grid location Y, and this is a decision that you have to make, right? So if you're considering, hey, I want to write some mapping software for Newfoundland, if you end up deciding, okay, I want to give people directions meter by meter, that may be a really hard problem to solve. There are so many different meters in Newfoundland, and who wants to listen to directions that are like every meter it tells you on the GPS where to go, right? So you have to decide on these, and it's an important decision. And also, which information is going to be stored in a node in your search tree, and we'll get to what this is. But you've also got to make a decision about, okay, maybe a node in the search is the current town location, maybe it has the action that I did, the distance or time driven so far, and we'll get to this a bit more as we come to that. So, a well-defined problem, meaning one that we can actually write an algorithm to solve, has to have a number of things, and this is a great exam question. So first, it has to have the initial state that the agent starts in. We have to know where we're starting in that environment. We have to know the actions that are possible from each state. So how do I transition between states in that environment? And what is that successor function, right? Like, is it deterministic, is it stochastic, etc.? Then we would like to know the set of possible goal states or a goal testing function so that I know once I've reached my goal that I'm actually at that goal. And also an action cost function. So when we get into just past satisfying problems, into optimizing problems, what we want to do is calculate the minimum cost of a solution. Because typically cost is bad. It's something that we want to minimize. And so if our solution to our problem is a specific number of actions, each of those actions is going to have a cost. We are going to sum up the cost of all the actions in the path from the start to the goal, and that will be the path cost or the solution cost. Okay? So we need to have all of these things in order to write an algorithm because the algorithm needs to know what to do. So here's an example problem definition for this problem that we talked about. The initial state is going to be St. John's. We are somewhere in St. John's. The actions are going to be, I'm going to tell you to move from one town to another town, and that's connected by a road, and I'm just going to assume that you're able to do that. The goal is either going to be St. Anthony or Port aux Basques, so it's a goal set of states, and the action cost function might be, let's say, total travel distance, or the time that it takes to get between those. But let's use travel distance. So this is an example of a well-defined problem that you could apply an algorithm. Of course, you also need the actual environment, the map of the environment, but that's assumed. So what is a problem solution then, once you've tried to make a decision about this? Well, it is a path from the start state to the goal state. And the path is an ordered sequence of actions. So in some cases, if I go right and then left, I'll end up in the same place, so the order doesn't matter, right? But if I, from right here, told myself to go right and then forward, well, that's a clear path. But if I said go forward and then right, I'm going to bang into the desk, right? So in general, a path is an ordered sequence of actions, and the order of those actions is going to matter. The solution cost is going to be the path costs. It's usually, and in this course it will be, the sum of the cost of all of the actions in that path. And what we're going to do in this course is make the extra assumption that the problems are going to say, okay, all of the costs of actions are greater than 0. Because if you have a problem in which actions cost less than 0 or equal to 0, then you can just take that action over and over and over and like make your cost arbitrarily low, and that's not an interesting problem, right? So we're going to say, yes, there is a non-zero positive cost to each action that you take, and that way minimizing it will actually mean something. And so if we talk about what an optimal solution is, then an optimal solution has the lowest path cost among all possible solutions. So there might be a bunch of different ways to get from the start to the goal, but an optimal solution has the lowest possible cost of all the solutions. And there might be more than one optimal solution as well. You can think, if I have to go right then up, well, up then right is essentially the same cost, and they're both optimal solutions to that problem. So let's look at an example of this. Here we have a graph. And so pretty much all problems that we are going to be considering are defined on a graph. And that graph has states and edges between those states. So if you've done graph theory before, then these are going to be called nodes and edges between the nodes. But nodes for our course are going to mean something a little bit different. If I show you the graph of a problem, then these are the states within that problem. So the agent could be at state A, state B, D, E, etc. And the edges between those are going to denote the cost of going from A to B. And if there is no edge between two states, for example, from A to E, there's no edge there, so I cannot directly go from A to E. So I'm sure you've all seen some sort of problem definition like that before. So in this particular case, our initial state is going to be state A. Our actions are going to be, you can travel directly from A to B. That is legal if there is an edge between them. So here, for example, going from A to D or D to E is legal. The goal state is over here in green. Apologies to colorblind people. It's hard to find so many colors. But over here in green, the goal state is state C. And the action cost function is the edge label. Okay, so the edges here is labeled again to go from B to D or from D to B. It's going to cost us 2. And for these problems that we're going to be looking at in this course, all the actions are reversible. So I can go from A to B, B to A, and back and forth and back and forth. This problem, if I gave you this problem on an exam and asked you to list all the properties of this environment, it would be fully observable because there's no hidden information. It is static, discrete, deterministic, single agent, and sequential. Now you could picture a version of this problem where it's multi-agent. So for example, if I have 2 agents here, and let's say the 2 agents are not allowed to occupy the same state at the same time. So one may have to go around the other. So we could turn this into a multi-agent problem. But for now, we're just looking at the single agent version of this. And so that's the type of problem that might come up on an exam, is to identify the properties of something once I've given you the problem. All right, so objectives in solving this problem. Different questions we might be asking in terms of solution is, A, is a path to the goal even possible? Can I get from A to C? Second, I might ask, what is the shortest path to the goal? Right? So these are different problems. They may have different solutions or similar solutions. So which algorithm should I use for this problem? By the end of the course, hopefully, you're going to have a bunch of different algorithms, and you're going to be able to tell me, hey, I would use this algorithm because of these properties and these properties of the solutions of those algorithms. And so what we're going to do first, for like the first half of the course almost, is search algorithms. And I'm sure who here has done a breadth first or depth first search at some point? So most people, everybody in the class has. So you're like, Dave, why are you telling us about search? We've already done breadth first and depth first search. Well, we're going to be doing a bunch of different search algorithms, and I'm going to be presenting them within this like unified framework so that all the algorithms, you will really be able to see how similar those algorithms all are. And how you can go uniform cost search, breadth first search, depth first search, Dijkstra, A-star, all of these algorithms are the same algorithm with just minor tweaks to them. So that's why I'm sort of going over something that you've probably seen before. So what is search? Well, each agent has several available actions that they can do at any given time. If at any point your agent has run out of actions, then there's no solution, right? Because they can't move from where they are. The agent can explore various sequences of those actions, so different combinations or permutations of those actions, and then the agent is somehow going to evaluate those sequences and then choose the best sequence that they found. And this process is called search. You look over a bunch of different possibilities and you choose the best one. And so searching will explore the problem's state space. Remember we talked about state space last time? We'll be moving from state to state in the environment, exploring all the different states that we can cover, and it will generate, so searching the state space generates a search tree. As we search new parts of the state space, we'll be generating a tree, and I'll have an example of that in a bit. And the search tree has nodes and edges. Okay, so let's have a look. Over here, in order to differentiate them, the problem space, the environment, has states, and the edges between these are the action costs and whether or not they're legal. Over here, I'm going to be showing in circles the nodes in the search tree. So a big thing that you'll eventually get used to is the difference between states in the environment and nodes in the search tree. So let's just have a look. So what are we going to do? Well, the first thing we do is we have a node, and that node in the search tree is the root node or the topmost node, and that represents us being starting in state A. Okay, so over there, this is a node, and it says we have started our search in state A. Next, what we're going to do is we are going to expand this node in the search tree. And what expansion basically does is looks at the possible neighbors, so the actions that we can do in this tree, and then generates nodes in the search tree based on where we can go in the state space. So just for example, if I expand state A, I have generated new nodes in the search tree, and the nodes in this search tree represent paths, not just states, but paths through the environment. So any node in the search tree, this doesn't just mean that I'm at state D, it means that I have to go all the way back up. So it means that I am at state D now, and I was at state A. So this represents the path of going from A to D. This represents the path of going from A to B. So what do we do now? Well, let's choose a node to expand. Choosing which node to expand is going to be called a search strategy, and that's going to be the second half of this lecture, and it determines which algorithm you're using. So let's just choose D randomly, because it's over on the left. We will expand this one by going to all of its neighbors, and again, this node down here represents a path from A to D to E, right? So it's not just, hey, I'm at E. It represents the path, and you may do things like store the cost of the path up to that point, etc. So we keep doing this process. We keep repeating and repeating. Maybe I choose this one next. Maybe I choose this one next. Here are all the successors or children or neighbors of this, and we keep going and we keep going and going. And we essentially keep going until we find our goal or we run out of time, right? Because it's a computer, we have to give it a time limit. We either found a goal or we've run out of time. And so this is the process of search, and these are nodes in the search tree, and these are states of the environment. And there's a reason I keep saying that, because it is a confusing point sometimes. And so just remember these squares over here, the problem or environment definition, that's the states, and then what you do while you're searching, those nodes you generate represent paths through the state space of the environment. So in problems that we'll be looking at, the state space is finite, right? So we only have 5 states in our state space over here in the problem. So that's going to be finite, but the search tree is infinite. Because if we were just to naively expand nodes here without being careful, we could go from A to D to A to D to A to just back and forth forever and ever and ever and ever, right? So the search tree of this particular problem is infinite, but the state space is finite. Here's another example. Who's ever played this sliding tile puzzle? Yeah, they're pretty annoying sometimes, but they're also pretty fun. It's sometimes called the 15 puzzle because it's actually 4 by 4, but I forgot to rename this slide, so this is the 8 puzzle, I guess. So the object in one of these puzzles is to get from some jumbled up configuration that someone has given you to one of a number of possibly different goal states. So in this example, you have to take this and change it to this, which is 1, 2, 3, 4, 5, 6, 7, 8 in order, and you do that by performing legal actions. And the legal actions in this problem are to take a piece, and if it has an attached or an adjacent blank space, then you are allowed to move that space into the blank space. And so you move it around, and you try and get it to here. So this is a problem just like going to Port-au-Basque, right? I've got a starting state, I've got an environment with rules, I've decided my legal actions, I've got a cost. In this case, it's a pretty trivial cost. Taking one move is taking one move. And so I might want to get to this state by minimizing the number of actions. And in order to do that, I will produce a search tree if I'm using search, and the outcome of that search will be an ordered sequence of actions that takes me from here to here. So an example of that search tree, if you visualize it for this game, if you go from here down to here, is you try all the different possible moves, you get this huge search tree, and oh look, down here we have found a solution. Now this one has a different goal because I stole the images from different websites. But in this one, it wants 1, 2, 3, 4, 5, 6, 7, 8 with the thing in the middle. But the problem is still the same, right? There's a goal state that we're trying to get to. And you can see that we may have dozens or hundreds or thousands or billions of these nodes in a search. Okay, so one of the only thing that remains is how do we select the next node that we want to expand in this search? And so let's talk about that. But first, I want to talk about in this, and whatever we do to choose that next node to expand, that's called the search strategy. But we're not going to talk about that yet. First, let's look at this search tree, and we have nodes over here, and you can see that I've labeled this node with an A, right? I've labeled this one with a D, but it actually does, this does represent a path. So how do we store that representation? Well, we're going to store a bunch of different data inside those nodes. So one thing we can store is the state. So this is the state that we are currently at this place in the search tree, so that's just the label. We are going to store the parent node, and so the parent node here is just stored as an edge, but we'll actually have like a pointer to another node that we reference in our code. So that's the parent node, that's the node that generated that node. We may also, depending if we want to know the path, for example, we may store the action that produced that node. We may store the path cost so far. So how far have I traveled from the start? So up here in our example, if I went from A to D, I could store A to D, that's 1, right? Or A to B would be 6, so I could store that. We will be storing that in the future, in a future lecture, and that's going to be called G. So G is the cost function so far. We may, depending on the algorithm that we're using, also want to store the depth or the number of actions that we've taken, which is different from the cost that we've traveled. And there may be other data that we store as well. And we can always do things like maybe we have some pre-computed data that we've done through some sort of optimization, etc., that we can store in the nodes. So maybe we could trade some memory for speed, etc. But we'll get into all those sorts of optimizations when we get to assignment 2. So again, node versus state, really important distinction. A state is a configuration of the environment, and a node is a bookkeeping data structure that lives in a search tree, and the nodes represent paths to that particular state that you're representing. So again, states, nodes. The next concept is called the fringe. So the fringe are the leaf nodes of the tree. So the leaf nodes are essentially the ones that don't have any successors yet. Okay, so at some point, we have expanded some nodes in the search tree. So here we've expanded A, and we've expanded D, but we haven't expanded these. And those are leaf nodes because, leaves in a tree are the lowest hanging things. And so the fringe is the set of nodes that have been generated but not expanded yet. And why is that important? It's because the fringe is the set of things that we have to choose from to expand next. And so we're storing that list of things. So the very first general tree search algorithm, what we've been doing so far is exactly this algorithm. And so in the optional textbook, it's called General Uninformed Tree Search, so I've just kept with that name. So we have this function, it's called tree search. You take in a problem and a strategy. And that strategy is going to be how you select which node to expand from. And so you start off with the fringe, and the fringe is going to be just initially the problem's initial state. So you construct a node based on the initial state of the problem. That's the root node of your search. And then this is the underlying search algorithm. So while true, so repeat this forever. Now in practice, you're going to have a time limit or something, but you repeat forever. If the fringe is ever empty, it means we have nowhere else to go. And we haven't reached a solution yet, so we return fail, no solution. There is no solution to this problem because we ran out of things to do. Otherwise, if there are things left in the fringe, we're going to set up this variable called node, and then we are going to take our strategy and use it to select a node to expand next from the fringe. So this is choosing the next thing to do. If the node that we chose, if the state that it represents is the goal, then we have a solution. And so what we do is we go back up through the parent pointers and we form the path to that solution. Otherwise, if we do have a new node and it's not the goal, then we expand that node based on the problem, which is the actions and stuff. So we expand that node, which produces a set of nodes, and we insert those into the fringe. So that's exactly what we just did, but it's in pseudocode form instead of visual form. What is node expansion? Because we looked at that, it's essentially looking at all the legal actions, generating the new nodes, and putting them into the fringe. So that function, expand, it's not very complicated, but what we do is we generate a blank list of successors or children or neighbors. Then for each action, in the legal actions of the problem from this node, we take, this S should probably be an N, but we generate a new node, which is, hey, state, do the action A, generate a node based on that, and then store that. So this is probably the most complicated thing, but it says, hey, if I'm at a current state, and I've said go left, just take the state, go left, and return the resulting state from that. So that's the state transition function. We are going to set the parent of the node equal to the node that generated it. Then the G cost of that node is going to get the previous node's G cost plus the action cost. We'll get into that in a little bit. We're going to set the action that generated this node, maybe set the depth of this node, and then add this node to the successors, and then return the successors. So it's a really simple thing. We essentially just loop over all the possible actions from this node in the search, generate all the states, generate the nodes from those states, and then add them to a collection, and then that's it. We've generated all the new nodes. Okay, so that's it. That's the algorithm. That will solve all problems if you choose the nodes to expand correctly. But before we get into the algorithms, we are computer scientists, so we want to evaluate the effectiveness of those algorithms, right? And there are a number of different ways to evaluate the effectiveness of different algorithms. One is completeness, meaning, is it guaranteed to find a solution if it exists? Is it complete in its search? If it's not complete, then we're actually not guaranteed to find a solution even if one exists. Optimality, does it find the optimal solution? If there is like a solution, can it find the optimal one? Time complexity, how long does it take to find a solution? That's important, we're interested in time. And space complexity, how much memory do we need to actually run the search? If one of these is way too long, then we can't even hope to use the algorithm. Time and space complexity are usually measured. You've all done big O notation at some point. So the n in the big O of n is the size of the graph, usually measured in nodes or edges, etc. Time measures the number of nodes generated, because depending on the problem, it may actually take a different amount of like actual seconds, for example, to generate the next node. So we eliminate that constant time factor and we just look at the number of nodes generated. And space is measured by how much memory is needed to store the maximum number of nodes at any given time. And so search and AI traditionally measures in terms of tree search, we have the branching factor, which is B. That's the maximum successors at any node, so branching factor B. The depth, D, which is the shallowest goal node. And so if we generate this big tree, at each depth we have B options, so it's B times B times B. So B to the power of D is approximately the size of our tree. So just as a quick recap so far, problems are defined by the initial and goal states, the action, and the cost function. The optimal solution has the lowest cost function of all solutions. Search finds a solution by exploring the search tree, which consists of nodes and edges. And remember that nodes in the search tree are not the same as states in the problem. And the problem-solving performance is measured by completeness, optimality, space, and time complexity. Okay, so that's the introduction to like what search is. Now let's talk about some different search strategies. And this stuff, this lecture and the last lecture are like the big, heavy exam question lectures. So if you don't get it right away, it's okay. Still follow along and review it later. So when it comes to search strategies, there are two overarching types of search strategies. One is called uninformed or blind search, where you have no information about the states beyond the problem description. So I know what the legal actions are and I know what the cost function is, but I don't know anything else. So for example, if I was here and I wanted to search in my head what might be the fastest way to get to that chair, something in my brain tells me going to the right is faster than going to the left. That is not uninformed search because I have some other information that tells me I should probably head in that direction. And so in uninformed search, we're limited to just successor generation and goal testing. So if I was doing uninformed search in real life, I would just test left, then test up, then test back, and you can start to see why that may not be so optimal. Yep.
So is that what ChatGPT is?
Absolutely not. We'll get into ChatGPT later on in the course. No, it doesn't do search at all. All right. Informed search, also called heuristic search, is about doing search but making guesses about which node to go to next. And hopefully those guesses are good and they make us go faster, right? So in real life, I would be like, hey, it's that way, I should probably go that way. But maybe halfway there, there's something I couldn't see that's an obstacle and I have to go all the way around, right? So maybe it led me in the wrong direction. So there's two types of search strategy. One where we don't know anything about where to go. We just have to try everything. And the other, which will be assignment 2, is this informed search strategy. So very first search strategy that you've all seen is called breadth-first search. So in breadth-first search, here's the English description of that. We expand the root node first. Then the root successors are expanded next. And then they're expanded, and et cetera, et cetera, et cetera. So it's the example that we did happened to be breadth-first search. So breadth-first search in general, if you want to visualize it in your head, all of the nodes at a given depth are expanded before any nodes in the next level. And to do this, we can just use a queue for the fringe. So in a queue, does anyone know what a queue data structure is? Yep. Yeah, so it's a queue. You know, if you're British, you've standed in a queue, right? So it's a lineup. It's first in, first out. So I get in a lineup, I wait to be expanded next, then I'm expanded. Then the next person gets expanded next, the next. So a queue data structure, however you choose to implement that, I'll show you how to implement it in JavaScript. But if we look at general uninformed tree search, this is the algorithm that we just looked at. In order to turn this into breadth-first search, here's the gigantic change that we have to make. Now it's breadth-first search. We just use a queue to store the nodes in the fringe. And then when we select the node from the fringe, it's going to be the first one, or the oldest one is more accurate, right? So the first person who got in line gets selected next, they get removed, and then the next person who got in line gets selected next. So let's have a look at that in practice. So here, This is breadth first search. So initially, we just have the root node, which is this node that's been inserted. Well, okay, the fringe now only consists of this one, so obviously we choose that one, and we expand it. So we expand D, and we expand B. Now, if I was smart, I'd have a visualization of the fringe. We have already expanded this node, so it is no longer necessary to expand that one. The next one that got inserted was D, so we expand D next. But we don't go down here because B was inserted first, so we expand B next. Then, okay, this one down here was inserted next. So what we're going to be doing in this class is using this grid world video gamey environment where we're going to do our search. And so breadth first search, looking from a particular location in a given environment, is going to look like this. We're going to search all of these, then all of these, then all of these, then all of these. So it's a breadth of search, breadth first search. It searches breadth first. Okay. So we're interested in these 4 performance measures of breadth first search. Let's have a look at it. Breadth first search is complete. That's really good. So if I put something in green, that's good. If I put something in red, that's bad. We don't want that. So complete is good. It explores the entire tree, and so it will find a goal node if one exists. BFS will find the shallowest goal node, since it explores all nodes at a given depth before the next depth. That's interesting. However, BFS is not optimal. In general, BFS does not produce optimal, cost-optimal solutions, since the shallowest node is not necessarily the optimal, the shallowest goal, that path is not necessarily the optimal path. BFS is optimal if the path cost is non-decreasing function on depth, or if all the costs are the same, right? If all the costs are 1, then of course the shallowest one is going to be the optimal one. So BFS is optimal if all the action costs are the same. Let's have a look. Well, if we did BFS, then we would find, we have to do this depth, then this depth, then this depth, all the nodes, breadth first. So as we did our search, we would come across C, which is our goal node, right? Because we went from A to B, and then we went from B to C. That is the shallowest solution path. But if we are trying to optimize these costs, the cost may not be optimal, right? So if we had looked over here, we could actually go from A to D, from D to E, and E to C, which would give us 7 instead of 11. So BFS in general is not optimal, but it is complete. It will find a solution. Time complexity. Well, that's the branching factor times the depth of the shallowest node. So each state has on average, so B is going to be an average here, B children. And consider a goal at depth D. Well, the first depth is going to have B. The second one, each of those B's is going to have B. And then each of those is going to have B. So it's B times B times B times B. So we generate O of B to the D nodes generated. Right? So if I ask you on an exam, why is the time complexity of BFS O of B to the D, you should be able to say something like that. The space complexity is the same because, unfortunately, we need to store the entire search tree in memory in order to be able to pick the next node to expand. And so the space is equal to the number of nodes generated, and so this is bad. So the reason these are in red is because these really exponential time complexities, even small problems, you get into 20 nodes and you already can't search it, or 20 states in the environment, and it's already very hard to search, right? So the space complexity and the time complexity, this is pretty bad. How bad? Well, let's have a look. This table, this is the depth of a search. Let's say we're going to assume that we have a branching factor of 10, meaning we have 10 actions at any given time. We can do 10,000 nodes a second, and we have 1 kilobyte per node, all right? So at depth 2, that's fine. That's just 1,100 nodes. It takes us a few milliseconds, and we use 1 megabyte of memory. But we just double that. We're at 100,000 nodes. That's now 11 seconds, and it takes 106 megabytes of memory. You just get up to 14 nodes, and we're already into times that we can't even imagine, right? So exponential time complexity is bad. We want to avoid that as much as possible. But even worse than exponential time complexity is exponential memory, right? I could probably run a simulation for 129 days. But I certainly don't have 121 or 101 terabytes of RAM to run it in, right? I have close to that in like disk space, but yeah, we're not quite there with RAM yet. So like this can be an issue.
Is it always necessary that there is always a constant b, that is the number of children of a node is constant?
So we take like the average or worst case usually.
Okay.
Yeah, but we choose some b. So for example, if we were analyzing chess, we would like look at a bunch of different games of chess, calculate the average b, and then use that. Because like at the beginning of a game, you have 10 different moves you can do, but in the middle of the game, you have like 60 different moves you can do, right? And the point here isn't to exactly get b correct, it's to show that it's exponential in time complexity, right? Okay. The next algorithm we'll look at is not depth first search, because I knew you all thought that was coming, but this is uniform cost search. So breadth first search is optimal when all action costs are equal because it expands the shallowest node, right? So if all the action costs are equal, then the cost is going down with the depth, and so that will give you the optimal path. Uniform cost search will be optimal for any cost. So it'll ensure us that we get the optimal solution. And so what uniform cost search is going to do is it's going to look through the fringe and choose the node with the lowest path cost so far and expand that. And so if all costs are equal, then this is equivalent to BFS, but in general, it's not. And it only works if all costs are greater than 0, et cetera, et cetera. You know, you could have an infinite loop if there's negative or 0 costs, so we're throwing those out. It's only positive costs. And if you've ever learned of Dijkstra's algorithm, which finds the shortest path between all goals or all states in a graph, then UCS is actually equivalent to Dijkstra's algorithm, but it stops when you reach that first goal. So if you know Dijkstra, you know uniform cost search. So here's uniform cost search. It's the same algorithm, except when we go to choose a node, we choose the one with the minimum G value. Same algorithm, we just choose a different node. That's it. There you go. Now you know uniform cost search. Super easy. Uniform cost search, I'm not going to go too deep into its time complexity. It's complete if B is finite. So of course, if we have a finite thing, we may never find a solution. But it's complete. It's optimal if all the action costs are greater than 0. So it will show the optimal solution. However, its time complexity, I'm not going to go into proofs in this course. But in general, it's way worse, right? If one algorithm gives us the optimal solution and one algorithm doesn't, it's usually the case that the optimal one is a bit slower. So if we have C star, which is the cost of an optimal solution, then the complexity is O of B to the 1 plus the ceiling of C star divided by epsilon, which is like has to do with the action cost. I'm not going to go into the proof of that, but I'm just showing you that the worst case is that's way bigger than B to the D, and the memory cost is the same. Okay, so uniform cost search is a way to get the optimal solution, but now our time and memory complexity are way bigger. So that's uniform cost search. Depth first search. Instead of expanding the shallowest or oldest node in the fringe, it is going to expand the deepest node in the fringe. The search goes immediately to the deepest level of the search tree, to a leaf node, and remember a leaf node is one that has no successors. And then if you want to visualize depth first search sort of in your head, once a leaf is reached, it is discarded, and then the search goes back up a level to search the rest of the children. So it goes down until it can't, then it goes up, then it goes down, then it goes up, then it goes down. And so the implementation of depth first search is to use a stack for a fringe. Now, in practice, it's more often implemented as a recursive function. It's kind of easy, but you run into weird problems like with stack overflows and stuff if you have big enough problems. So we're going to show, at first, at least, the stack implementation. So this is depth first search. Breadth first search, depth first search. Breadth first search, depth first search. So hopefully you weren't taught it in this way before, because they're the same algorithm, but they select a different node from the fringe. That's it. Search is just looking at everything. You just have to tell it what to look at next. So here, this is obviously I call this the iterative version, where you have a fringe that you're taking from. But you may have seen this in its recursive form, which is the recursive depth first search. So you have this DFS function that you're going to call recursively. So you get passed in a node. If the state of the node is a goal, then you've got your solution, so you can stop. Otherwise, you generate the successors of this function, or of this node. Then for each of the successors, you call DFS on the successor again. Okay? And then what you do to start this process is you call DFS on the root node. And again, when I pass problem into something here, that's just the properties of the problem. So it dictates the legal actions, etc. That's not an actual thing that you would pass in if you were writing this. So depth first search, it just search a node. Is it the goal? No. Generate my next nodes. For each of them, go down into the tree. And if you run out of successors, then the recursion is going to pop up and do the previous or the next one from the previous depth. The performance of DFS. Oh wow, that's bad. It's not even guaranteed to give us a solution. It might enter an infinite loop. In our problem, I could go A, B, A, B, A, B, A, B, A, B forever and just not escape that loop. So enhancements to it, we'll see later that we can do something to make this a little bit better, but in general, it's not even complete. So if it's not complete, what does that mean about optimality? Well, it's certainly not optimal, right? If it might not find a solution, it's certainly not going to find the best solution. Because any goal that it finds could literally be anywhere in the tree. It could be the worst solution. It could actually be the worst solution. And in practice, it often does look like the worst solution. The time complexity, however, is worse than BFS because it could go infinitely. But M here, that is, M is the maximum depth. So it could find the worst solution. So for BFS, D was the shallowest depth of a solution. Time complexity, B of M, is way worse because M might be the worst solution. However, DFS has one redeeming quality, and that is its space complexity is excellent because we only ever have to store the current path. We don't have to store the whole tree because I'm only drilling down through all the actions, and only if I come back up do I then select the next action. So the space complexity is excellent. It's linear. We've got out of the exponential realm. And so where M is the maximum node depth, that is the linear factor on B. And so it only has to store successors of nodes in the current path, not in general. So that's why DFS is good. Here's a little look at DFS going through a maze. And you can see this sort of backing up behavior. It goes in whatever direction that you've set it to go in until it reaches a dead end, and then it backs up and it tries the next successors. Okay? I don't need to let that play out all, but eventually it reaches the goal. Now you might say, but Dave, you said that this could loop forever, right? So why didn't it just go back and forth, back and forth, back and forth, back and forth? We'll get to that at the end of this lecture. But that's sort of a visualization of what DFS can look like in practice. All right, so DFS can infinitely loop. How do we prevent it from getting lost in the search tree or infinitely looping? Well, we can come up with an algorithm called depth-limited search. Instead of depth-first search, depth-limited search. And all we're going to do is use DFS, but apply a depth limit to the search. So we're going to choose some limit, call that L, and then we're going to just say the search stops after L. Okay? So we could do this in a number of different ways. You can just say if depth is greater than L, then stop, or you could say there's no successors past L or whatever. This solves the infinite path problem because it will search the entire tree up to depth L, but nothing more. So we can't go AB, 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 AB. If our max depth of L is 4, it will go AB, AB, but then it'll stop because we've already gone 4. Okay, so that's cool. But it introduces a new problem, which is that even though it will search all the way up to L, it will never go past L. So if the solution is at a depth that's bigger than L, we will not find that solution. So that's unfortunate. However, the time complexity gets a little bit better because we're only searching a number of nodes up to L, or sorry, up to b to the power of L. That's better than the worst possible thing. But the space complexity is, again, amazing. Like, that's what DFS has going for it. It's the fact that we have b times L rather than b to the power of L for our space complexity. So, if we want to implement a recursive version of depth-limited search, everything past, like all this here, this was depth-first search. The only thing we have to do to get depth-limited search is to add in this one extra check, which says if the depth of the search is greater than L, then stop the search. It will unroll the recursion back up to the parent node. And then how we call this is, like before, we call, instead of DFS with just the root node, now we have to pass in the root node and a limit that we have to stop at. Well, now the next question is, how do we choose L? Right? That's obviously a huge thing. We don't want to go too short because we'll miss the solution, but we don't want to go too far because then we'll calculate a whole bunch of stuff that we don't need to. And so there's a bunch of different ways that you could choose L. Like, for example, maybe I'm here and I'm moving in meters. So that chair is what, 6 meters away? So maybe I choose L to be 7 so that I know I will find a path to that chair. So that's some sort of analysis of maximum path length. Maybe we'll do that. Maybe we know the diameter of the search space, right? Like, I don't know the distance, but maybe I know, okay, someone told me that this, it won't be more than depth 20, so maybe I'll choose 20. Or maybe it's equal to the number of states in the problem. Like, if I only have 5 states in my problem, then the optimal solution is probably less than 5 actions, because why would I ever repeat states in a search? All these things are fine, but let's let the search figure it out. We can also search for L. How are we going to do that? Well, this is another algorithm. It's called iterative deepening depth-first search. Iterative deepening means we keep going further and further when we search. So the main idea is to gradually increase the depth limit. So we're going to set L to 1 and then run a depth-limited search. If we didn't find a solution, set depth to 2, then run a depth-limited search. If we didn't find a solution, so on, until we find a solution. And so the goal will be found at the shallowest depth D. But the reason for that is because we haven't found any solutions from 1 to D minus 1. If there had been a solution that's shallower than D, then we would have found it. So whenever we find a solution, we know we're at the shallowest depth for that solution. So this means that iterative deepening depth-first search has the completeness and optimality of BFS. So it is guaranteed to find a solution, and it's optimal if the action costs are the same, but in general, it's not optimal. But it has the space complexity of DFS. Aha. So we've taken the good things of BFS and the good things of DFS and created one algorithm that does both of those. However, you might say, well, if we're going from depth 1 to depth 2 to depth 3 to depth 4, that seems like a lot of wasted computation. How can the time complexity be the same? Right? Well, turns out it is, because whenever you're dealing with exponentials, right? So say this is depth 1, I search one thing here. Depth 2, I search 2 things, because I'm doubling it. Depth 3, I'm searching 4 things, I double it again. I keep doubling, I keep doubling, I keep doubling. And 2 is I'm showing 2 here because that's the least amount of branching factor. It could be way bigger than that. But the point is, the way the mathematics work out is that even if you have 2, the final depth always has more nodes than everything else combined. And if you have exactly 2, always, then the final node, the final depth down here, will have exactly n plus 1, where n is the sum of the previous nodes. So because it's exponential, the last depth is the only thing that matters, and so it's still, in practice, you're doing about double the amount of work, right? But it's still the same time complexity because we know how time complexity works. So the time complexity, even though we have d to the b, and then d minus 1 to the b squared plus blah, blah, blah. It's still only the highest exponential that matters for our big O time complexity. So it has the same time complexity as BFS, even though in practice it does about double the work. It has the same space complexity as DFS, which is linear instead of optimal. So in practice, it takes about double the amount of time, but it's way preferable because we could actually fit the thing in memory. So remember when I said for BFS, I could probably run something that takes 100 days, but I don't have 100 terabytes of RAM? Well, I would need a few kilobytes of RAM to do this one. So that's why we would choose something like that. So recursive depth-limited search looks something like this in its full form, where we check this cutoff just tells us whether or not we have found a solution up to this point. So I'm going to say cutoff occurred equals false. That's going to be set to true if we have searched everything up to L. So if the state is a goal, then I've found a solution at its shallowest depth, so return that solution. Otherwise, if the depth of the node is greater than or equal to L, we return that we have a cutoff, so we have searched everything. Then, if that has not happened, then we expand all of the neighbors of this node, and then we call DLS on the child, the limit, and the problem. If the result of that was a cutoff, then a cutoff occurred equal true, and if the result was not equal to fail, then we return the result. Okay? So this essentially just does that. Okay, if we're searching up to a given limit, we have either found a solution, or we have run out of things to search, or we have reached a depth cutoff. Okay? We're going to actually use that because if we found a solution, we can stop the search. If we reached a depth cutoff, it means that I have to go one deeper. But if I have legitimately run out of things to do, then I know that I can stop my search because I've searched the entire problem space. So those are the three possible outcomes of a depth-limited search. And then iterative deepening depth-first search is just iteratively calling that function. So iterative deepening depth-first search, for d from 1 to infinity, or your time limit, you start at depth 1. You call DLS with the root node and d, which will initially be 1. If the result was not equal to a cutoff, meaning that if we found a solution or we searched everything, which means there is no solution, then we return that result. Otherwise, it doesn't actually say an otherwise here, but if that is not true, then we just go to the next depth. And we go to the next depth and the next depth and the next depth. So if the first solution is at depth 6, we'll find it at depth 6 with this algorithm. So if we compare all these search strategies, right, we have this nice table of results. And so this table of results, I'm going to highlight the good ones here. So BFS, it is complete, and it is optimal if all action costs are equal. Uniform cost search is complete, yes, if B is finite, and if action costs are greater than 0. And it is optimal only if, or it's always optimal, sorry, so that's good. Iterative deepening depth-first search has the same properties in completeness and optimality of breadth-first search, but it has the space complexity of depth-first search, which is great. So that's what we want. So that's why, in general, we may want to use iterative deepening depth-first search instead of breadth-first search. We will not be actually implementing iterative deepening depth-first search in an assignment, but theoretically, you would have to know, for example, why would I want to use that over breadth-first search? That's a great exam question. Okay. So just a quick note that I'm about to talk about two different algorithms. One is called tree search, which we have been doing. Another one is called graph search. That's just what they're called in the book, but they're essentially the same algorithm. And I know there's a lot of terminology. I've thrown a lot of algorithms at you. I don't expect you to all remember them right now. But when you go back and you look at the differences being one line of code, it's actually pretty easy to remember all the algorithms, and you'll get surprisingly familiar with them. So in this book, which is an optional book, these are the names that they're using. So if you want to follow along with the book, you won't get lost. But the names are not important, sort of the concepts are. So we looked at that example of depth-first search going infinite, right? Going from A, B, A, B, A, B, A, B. One of the most important ideas in search is how to avoid that. We don't want it to go back and forth, back and forth, back and forth. And this is especially important in environments where you have reversible actions, meaning I could move to the right and then I could move back to the left and end up in the same spot. So most infinite loops and wasted time can be avoided by simply not returning to states that we've been before, right? If we think about the properties of our environment, would an optimal path ever visit the same state twice? Right? Like if it has a non-zero positive action cost, revisiting that state would just add to the cost. So by definition, if we go back to the same state, we have a worse path. So this is the idea here. So we can remember nodes that we have expanded and then don't expand any other nodes that have the same states as those nodes. And this can lead to an exponential savings in the number of nodes generated. Saving exponentially is exactly what we want. And the way we're going to do this is implement something called the closed list. So the closed list is just a list of states that we've already expanded. That's it. We just keep track of all the nodes that we expand, and we write down the state of that node so that we know never to create another node with that state. So the closed list stores expanded states, not nodes, but states. It is often implemented as like a hash table or a dictionary for efficient lookup, but we could just have a vector of all the possible things that we've seen. And so what we're going to do is just check to see if if the state of a node is in the closed list before expanding it. That's it. So what we're going to do, because this is called the closed list, then the open list is going to be the fringe of unexpanded nodes. So the the fringe that we've been talking about so far, we're going to call that the open list from now on. So we have the open list of things that we want to expand, and we have the closed list of things that we've already expanded. And in practice, in assignment 2, we're going to be implementing this open list as a priority queue, which is sorted based on our search strategy. Okay, so this is what we just did. That's the exact algorithm that I had on the other slides, but as foreshadowing, I just included some white space here. So this is the algorithm. We have an open list. That stores all the things we haven't expanded yet. While true, if we have nothing left to do, that's a failure. Otherwise, I select something from that open list. If that's the goal, return the solution. If it's not the goal, expand the node and add it to open. In order to add a closed list to this, all I have to do is add some sort of data structure for the closed list. Maybe it's a set, maybe it's a dictionary, maybe it's just a vector, whatever, doesn't matter. And down here, if a node is not the goal, before we expand it, check to see if the state of the node is in the closed list. If it is, then continue. So that means that don't expand the children of any node whose state is already in the closed list. And if that is not true, so it's not yet in the closed list, right before we expand it, add it to the closed list. That's it. So we're just checking to see what we have done so far and don't do it again. So this is that algorithm now. We added a couple of lines, but it's not a huge leap to get to this point. And so the book calls this thing graph search. So we called the other thing tree search, right? So it's searching a tree. This is still searching a tree, but the book just calls it graph search. So I'm just going to leave it as graph search, and just know that graph search means closed list. If on an exam I were to ask you a question, I will say tree search without a closed list or graph search with a closed list. Like, I'm not trying to trick you up on that terminology. I'll be very explicit if I'm asking you a question about whether or not there's a closed list or not. So it's only called graph search because that's how it's described. It's still an algorithm that searches a search tree. It just uses a closed list to avoid searching of nodes that represent the same environment state. So in assignment 1, what you have to do is, and I'll get into assignment 1 in the next class. I'll show you exactly how to set it all up. But what you're going to do is you're going to use Dave GPT, because I've given you the solution to the assignment. It's right here. You copy that, you paste it. I'm not joking. You copy and paste this into your assignment, and then you turn it into JavaScript. That's assignment 1. And then do it again for DFS. But a really cool thing is you can do it in a way, like you can think, so as part of your algorithm, you're going to get this configuration object. Inside the configuration object will be a search variable. That search will either be BFS or DFS. So you could think that you would go, okay, if strategy equals BFS, do all of this. Else, if strategy equals DFS, do all of this. Or you could do it the way I'm going to ask you, and only one line needs to change. So you could just write the algorithm and then have the if statement around that. Okay? Now technically, in JavaScript, you would not change this line of code because you can just use a JavaScript array. That's fine. But down here, in JavaScript, open.pop gets something from the back. Okay? So that would be a stack. So open.pop would be DFS. And then open.shift in JavaScript would be BFS. It's literally like 4 characters of code difference between BFS and DFS. And I'll show you exactly where that goes in the assignment. The assignment is going to have a user interface. You don't need to worry about that too much. It's just for debugging. And you will implement both DFS and BFS, and you'll be able to see it beautifully visualized and all sorts of stuff. So tree search remembers nothing. It will re-expand states multiple times. That is bad. Graph search remembers the states that you visited and will never re-expand a node that has the same state as one we've expanded before. And so again, just to drive it home, tree and graph search, just a name. One has closed list, one doesn't. That's the important part. So what is the complexity of this? The time complexity. Holy crap. Well, it still retains the same. Well, okay, let me just go in the order that I have the slides. The time complexity is now amazing. If we cannot re-expand a state, then it's just the size of our problem, right? So if we have 5 states in our problem, then the time complexity is big O of the number of states, which is insanely good. So each state is expanded at most once. So in the worst case, we're going to expand every state in the environment. And in most cases, that's far less than the big search tree that we had before. And it's going to be the same upper bound no matter which search strategy. So if that's BFS, if that's DFS, if that's UCS, if you don't re-expand the states, then you're good to go. The space complexity is also big O of the number of states, right? So we have to store the entire search space in memory, but the amount of nodes that we generate is just equal to the number of states. So it's better, but this is often sometimes still a bit too much. Like if we have every square meter of the Earth, that's still a bit too much to have in RAM, but it's way better than what we had before, right? But if I'm using a search strategy like DFS, then it has the search complexity of either big O of the number of states or DFS, whichever is less, right? So whichever search strategy you use, that one is still going to be the overruling space complexity factor. However, graph search may no longer be optimal. Whereas if you had an optimal solution before, this one may no longer be optimal. It is a very tricky thing to describe because it depends on the underlying algorithm. Once we get into the A-star algorithm, I'll be revisiting this issue. But when a repeated state is detected, that means that the algorithm has found another path to the same state. If it finds another path, that path may actually be a better path. But we've already found the other path, which is worse, and we've told it not to revisit it, right? So that can be bad. So graph search keeps the original path and discards the new path. But the new path may be the better path. So it's only optimal if we can guarantee that the first solution found is the optimal one. So that means uniform cost search, that always works. Because if the first thing that we find is the optimal one, then it's still optimal. But with BFS, it's not necessarily the case unless the action costs are the same, right? So if I ask you, hey, graph search with the closed lists may no longer be optimal, when is it actually still optimal? So that's a problem. It still maintains the completeness property, but it may not be optimal. So there's always these trade-offs in search between memory, time complexity. When we get into heuristic search, there'll be all sorts of new trade-offs that we have. But this is basically all you need for assignment 1. And in the next lecture, I'll show you how to set up assignment 1, how to do it. And you only have a week for assignment 1, but it's like 20 lines of code. So assignment 1 is all about getting used to the assignment infrastructure. And then every subsequent assignment will be the exact same infrastructure. And so then you'll be used to that. So assignment 1 is kind of easy algorithmically, but you may take a while to get used to the programming interface. Thanks.